right? Let's look at some other ones. These become more involved, especially because you don't have y equals something. You have x equals something. And that's when people struggle as far as what does that really look like, okay? So let me show you something that you can do. You're used to seeing x, y graphs that look like this. But what I want you to now know is that when you have things written in terms of y the way these are, your y is actually your input and your x is your output. Now we're going to pick some numbers that the way you kind of used to do in algebra 2. You could pick like 0, -1, -2, and 1 and 2 and see what the other one would spit out, right? So now if I put in -2 here, what would I get? Say again? A 1? A positive 1, right? So you're going to get, what is this as a point? This is the confusing part. It's 1, -2. So at 1, -2, you'll plot a point. If I put now -1 right here, where y is at, what am I going to get? 4, right? Which is 4, -1 as a normal point to graph. You see how I'm doing this? So 4, -1, 2, 3, 4, -1 goes here. 0 will yield 5, so it's 5, 0. And then 1 would go back to 4, which is 4, 1. So this time it's 4, +1. And then finally you'd get 1 here, as far as 1, +2. And the graph looks something like this. Yeah.
Could you just do the thing where you turn your head before and then...
So yes, and this is what I want to eventually, I want you to get to that, turn your head, but if you can't see it, some of them it's easier to see, especially with the quadratics, because they have a symmetry about the y-axis about them. But some that are with the linears, they're hard to see actually, believe it or not, if you try to turn your head. So this is what I'll say to that. If I looked at this one, and I don't know what the graph looks like, and I don't have time to do a table, another thing you could do is switch the x and the y, or, I'm sorry, that's for inverse functions. You just want to solve for y. You know what I mean? So you get 5 minus y squared. Let's get y by itself. So I'm going to add this over because I hate those negative coefficients. And then I'll get negative x plus 5. You with me? Now, what would I do next to get y by itself? Square root. So when I do that, I'll get a plus or minus square root of negative x plus 5. For transformations, for you to be able to see what's going on, I've taught you that you have to get this coefficient to a +1. So if I factor out that negative, this is what I really have. And now if you look at this like a parent function, you know the square root of x, it starts off to look like something that looks like this. Well, this one has a negative square root of x as well. Okay? Now let's go through the manipulations of the transformations. This negative says it would reflect across the y-axis. And then finally, this one says it would move 5 units to the what? Right, because everything is opposite of what you see. And that's how you get to the graph that we got with the table. You with me? All right. So let's do this other one. You can do this one a little bit easier because this you just solve for y. And y is equal to x plus 1. And if you graphed x plus 1, it's just the slope that has the y-intercept at 1. Pretty easy, right? But the whole turning your head to the right, if I looked at the original 5 minus y squared, I can treat that almost like a 5 minus x squared. You know what I mean? Because I know what this graph looks like. But then turn my head, see the quadratic being flipped down, and shift it up 5 units. If you can see that, fine, use it. Otherwise, use the table that we talked about, or use this solving for y that we talked about with transformations. Okay? I think more people will lend themselves to the table. All right, let's go ahead and finish this one out, though. Step 1, dy or dx, what do you think? dy, yeah, because you want the red on top of the blue the entire time. So let me highlight in orange the top function. This one's on top, and on green the bottom function. So this is on top, per se, the entire time. We have to rotate our head to see this one, don't we? Dy's, we have to rotate our head so that we can see that orange function is on top of the green the entire time. Now, these points are points of interest, of course. So I would set 5 minus y squared equal to y minus 1. Again, I don't like these negative coefficients, so let me move everything to the right. Y squared plus y. Subtracting will give me a negative 6. Factoring is y plus 3, y minus 2, so that my solutions are at negative 3 and 2. You with me? So y is equal to negative 3 to 2. Low y to high y. You with me? Because this is a 1, 2, 3. This is y equals negative 3. And if I put it as a coordinate point, it would look like this. And this one would look like a y value of 2. Okay, let me highlight it in green. From negative 3 to 2, those are the corresponding ones. Okay? Now, if I put negative 3 into any one of these functions and solve for its x value, I'd get negative 4 here. If I put negative 3 over here, or sorry, a 2 as a y value, I'd get 1. So the values are negative 4, negative 3, and 1 and 2. But again, all we care about are what? The y values. Okay? So now we got to determine what's the top function. Anyone, what's the top function that you see? 5 minus y squared. Okay, so just like we said, it's going to be 5 minus y squared is the top function. Okay? Is this one right here. And it's going to be subtracting the bottom function. What's that one? Y minus 1. Notice my use of parentheses, guys. And also, let me highlight it in green, this bottom function. Notice the use, notice that it's in respect to y. So that the functions that you write in here in the integrand need to be what? In terms of y. And what does that mean again? That means we solved, which this was already conveniently solved for us, we solved for x. So when you get x all by itself, you get all this stuff in terms of y. When you get x all by itself, you get all this stuff in terms of y. And then that you could just simplify out and do it by hand, just like normal, like integration. So like that would be from negative 3 to 2, negative y squared minus y plus 1. So it's going to be plus 6 dy, and then integrate like normal. Okay? Yeah?
So basically, you only do the table in order to draw the figure?
Just to draw the figure. After that, you can eyeball it and figure out. Yes, the table is really only used for the drawing of the figure. So you can figure out what the top and the bottom is. Okay? Alright, so we have x to the 6th. It's like a quadratic, only the bottom of the base is more rounded. And if it was x to the 8th, x to the 10th, it would get fatter and fatter on the bottom. This right here is a normal linear translated 2 units up. And we want to find the shaded region. So all of this right here. Alright, we want to find the shaded region, and these two words will make you kind of happy because you know you're going to be able to use what? Yeah, this will be with calculator. So, right off the bat, we need to find these points of intersection because we need their what values? X values, because this is going to be a dx. Okay? Nice. So we need their x values. So if I do x to the 6th, you'll do this menu solve feature, which let me just go ahead and show you how to do that real quick. You'll from here press menu 3, 1, and then you're just going to do x to the power of 6 minus x, because I set those equal to each other. I moved them over, set it equal to 0, comma, x, and I get this. How many decimals do I need throughout a problem from the experience? 6. So to get all 6, go up, press enter, 214862. So we'll go 1.214862, and then the other one was our negative 1 right here. So you have a negative x, or negative 1 for x. So this is that negative 1, and this one right here is the 1.214862. You with me? What's the top function? No, the top function is this guy. And a lot of people think that that's the top function because it has the biggest degree, but the top function is actually x plus 2, and you're going to be subtracting what? X to the 6th. And putting this into your calculator, what would you get? So we get, here we go, the integral, and it's going to be from negative 1 to 1.241, is that right? To 14862. 14862, and it's going to be the top function, which was x plus 2 minus x to the 6th. Right? We kick down and then close it up, and this is going to be x. Control enter, and I have this set because of Calc apps. 3.967 if I round, or 3.966 if I truncate. I'm a rounding kind of person, so 3.967. Approximately 3.967 units squared would be the answer on this. Yeah. We good? The last two, actually this is one before the last slide. I have two shaded regions. And to me, I think what makes this easier is if I separate my functions. That is a cubic one, which is right here. And this one is the quadratic, which is right here. How many integrals? First of all, what do you see, dx or dy? I see dx. We see dx because those are the vertical slices saying red's always going to be on top of blue. So let's set this one up first because there's going to be two integrals if you haven't noticed already. What is the low bound? What's the low to high for this first one that I've started off? Perfect. -4 to -1 because all we care about are their x values. What's the top function?
X cubed.
X cubed, right? It's the red one. X cubed minus 6x minus, what's the bottom function? 8 minus, again, with those parentheses, they're very important. And then dx. That's the first one. The second one that we would add to this is going to be dx or dy? Dx, right? Because blue now is on top of red the entire time. It's not going to be dy because if we did dy and we were going horizontal, look at this blue on top of blue piece right here. You can't have that. Everything else is blue on red. Actually down here you still have red on red down here. You see that? So you want to go with one that has the same function on top throughout the whole thing. So this is going to be another dx. And what's my balance? Yep, from -1 to 2. And what's the top function? 8 minus 3x squared. Minus the bottom function, which is x cubed. So you can break it up and definitely set up. And these are nice because you have set up but do not evaluate. So they're looking to see, do you have the correct dx's? Let me highlight it. Do you have the correct dx's? Do you have the correct bounds? And then of course, do you have parentheses correctly with the top and bottom? Because subtraction has order. Okay, so you can't just subtract whatever you want. and get the same answer. Okay? But that's a setup and do not evaluate, which are cool. The last one is here. We're about to go to pep rally, so I will record this on my own after school and then post it online to let you have it. Or we could start in class tomorrow by looking at this. You know what I'm saying? Because your CFA on day one stuff is not until, because your B day is with eighth period, is not till what, Friday this week. Okay? Okay, so let's go ahead and finish this video. What we're going to do is we're going to find the differences between solving something working it with x's, such as dx, vertical slices, and then versus y's or dy's, which are horizontal slices. Okay, so we have x squared, okay? And just so that you can visualize it a little easier, that's the x squared right here, as well as here on both of them. And blue will do the linear function, y-intercept of 18 with a slope of -3 on both of them. Okay, so our intersection and point of interest already has been found for us. It happens at 3, 9, and then our x-intercept is at 6, 0, and then our y-intercept is at 0, 0. And we're trying to find with the bounds revolving around the x-axis as well. So here's our x-axis, here's our x-axis, so that our shaded bounded regions become this, as well as this one over here. Okay, so we're going to look at the similarities and differences between working with x's versus y's. Alright, so if I'm going to do vertical slices, dxy's, let me get color on that. We're going to have vertical slices. It would be like all these are vertical sliced, and I would stop here, and then I would do vertical slices again and have two different sections. The reason why I would have two separate integrals if they're dx is because of the fact that we have two different tops over bottoms. Okay, so we're going to have two dx's that are going to add together, and let's analyze what I'm talking about. If I looked at this first shaded region, my top function is this red one here, which is the x squared, and my bottom is the x-axis, which is just 0. So you could say the top is x squared minus the bottom of 0. Okay, and it would be from 0 all the way to 3. From here to here, it would be from 0 to 3. So we'll say 0 to 3. This next one, which I'll highlight in orange, the reason why we have to partition into two different, or break up into two different integrals is because now the top function no longer is x squared. It's actually the blue 18 minus 3x function. So we're going to say 18 minus 3x is the top, and now 0 is the bottom. Okay, and that one's going to be this time from 3 to 6. So this is a setup, but do not, actually, no, this is not a setup, but do not evaluate. So we would actually solve this all the way out. We have x squared from 0 to 3, which will be added to 3 to 6 of 18 minus 3x dx. And then you just solve them out independently. This one would become x cubed over 3 from 0 to 3. This one would become 18x minus 3x squared over x squared. Actually, not over x squared, over 2. So x to the 2 over 2, and then multiply that constant multiple of -3 back in, and you get from 3 to 6. So solving this all out, you could get your answer. The other way would be if I worked with y's, horizontal slices. And you see throughout this entire low to high, which in this case is going to be from my lowest y value to the highest y value, you can say from here to here, we're going to set it up as 0 to 9, and remember we have to solve this in terms of y, meaning we're looking for my x variable to be all by itself, which I'll go ahead and change. This one is a plus or minus square root of y, And this one is, let's go ahead and do it. 3x is equal to 18 minus y. Therefore, x is equal to 6 minus y over 3. So now I solve for both my functions. Let me highlight it while I say it. In terms of y. Okay? And those are the functions that are going to go in here as far as the top and bottom. So looking at this, this is where I rotate my head. Okay, so I did not rotate from 0 to 9. I looked normally straight up and down from 0 lowest y to the highest y because I'm integrating all that interval. But I do have to rotate for the top minus bottom part. Okay, I have to rotate my head and figure out which one's the top function. So when I rotate my head 90 degrees, I'm going to highlight in green right now. This right here becomes my top function over that entire interval. Okay, and that top function is this function here, but we have to write it in terms of y. So it will be, the top function is 6 minus y over 3. Now the bottom function I'll highlight, let's say in yellow. Again, having rotated my head, the bottom function on this interval is going to be this piece right here, which with the red it's correlating to the x squared piece. And again, after solving for it in terms of y, we're going to look at the positive square root of y, not the negative, because the negative square root of y would actually extend further over here. It'd come all the way over here. That's the negative square root of y piece. But the positive square root of y is only looking from the origin up like this. And that would be the setup on that. And then you would just by hand finish off the rest as far as integrating and doing your normal rules of differentiation from 0 to 9, and you'd get your answer, and they both will be the same. So that's the differences between dx and dy as far as horizontal or vertical slices. And as far as like, what do you write it in terms of? If you have it in respect to x, which are the vertical slices, the integral must be, or the integrand must be in terms of x, just like these two. And then if you have it in respect to y, the integrand functions must be again in terms of y.